Alright, this is day number 4 on LHopitals Rule and indeterminate forms. Wouldn't it be great if we had a way that we could just evaluate limits that came out to be 0 over 0 without having to do all the conjugation or factor and cancel? Well, we do now, so hold on for this ride. Alright, so I'm just going to kind of give you the gist of what's going on here. I'm going to scratch all this stuff. LHopitals Rule applies to these forms. 0 over 0, infinity over infinity, infinity minus infinity, 0 times infinity, infinity to the 0 power, 0 to the 0 power, and 1 to the infinity. Okay, and so what LHopitals Rule says basically is that if you have a limit as x goes to some value, right, let's call it c, of f of x over g of x. So this is assuming you can get this this limit into this form, f of x over g of x, equals any one of these up here, then this would be the same as the limit as x goes to c of f prime of, this should be f prime of c. Right? And it's c and c. This would be the same as f prime of c over g prime of c. So all that means is, like, if you run into a stumbling block here, take the derivative of the top and the bottom. However, the biggest fail that most students have is they use the quotient rule. This is not the quotient rule. No, not the quotient rule. All you're doing is taking derivative of the top and the bottom separately, and then you're going to then evaluate and plug in those values. So let's take a look here. The first thing you got to do is you got to evaluate at the limit, right? So let's plug in 0. So sine of 0 over 0. Well, that's 0 over 0. You have to say that it's an indeterminate form. Those 7 forms that we saw on the previous page are indeterminate forms. Therefore, I'm going to take the limit as x goes to 0 of the derivative of the top and the bottom. Derivative of the top is cosine x. Derivative of the bottom is 1. So now I have the cosine of x over 1. When I evaluate that, the cosine of 0 is 1. Divided by 1 would be 1. And look, that's one of our special limits, right? Doesn't the limit as x goes to 0 of sine of x over x equal 1? There you go, LHopitals Rule, you are our friend. Okay, let's look at the second one. If I plug in 0, I get 1 minus cosine of 0, which is 1 over 0. So I get 1 minus 1 over 0, which is 0 over 0, which you need to write indeterminate form. And then I would probably do this. I would write, L'Hopital is applied, so the limit as x goes to 0 of the derivative. So what is the derivative of 1? It's 0. Derivative of negative cosine is positive sine. Derivative of x is 1. And then I do a direct substitution. So this would equal sine of 0 over 1, which is 0. That's our other special limit. Okay, here's a funky one. Negative natural log as we go to 0 is negative. I'll think about natural log for a second. As the natural log comes to 0 from the right, it's going to be negative infinity. Okay, and the cosecant of 0 coming from the right is also infinity. That you can check on your own, but that would be an indeterminate form as well, right? Infinity over infinity. Okay, that's an indeterminate form. Therefore, I'm going to take the derivative of the top and the bottom. Okay, so I apply L'Hopital's rule. So I have the limit as x approaches 0 from the right. The derivative of negative natural log of x is negative 1 over x. The derivative of cosecant is negative cosecant x cotangent x. Okay, so now I'm going to evaluate those. So what I would actually do here is I would take and bring this -1 over x. Okay, first of all, let's get rid of that negative because that'll cancel. Okay, and cosecant x is the reciprocal of sine x. So I bring the sine up top, make it its reciprocal. And the reciprocal of cotangent x is tangent x. Now I'm going to write that tangent x as sine x over cosine x. Okay, and we've got something we can kind of do here, a little sneaky, but that right there is going to be 1. And here, this will be, what will that be? If I do direct substitution, that would be sine of 0 over cosine of 0, which will be 1 times 0 over 1, which will equal 0. So the limit of the original is actually 0, even though it seems at first to be potentially that it does not exist. Okay, last one. Let's see what we get here. If we plug in a 0, we get 0 times the natural log of 0 coming from the right, which would be 0 times negative infinity. That is an indeterminate form, but how can I use LHopitals Rule if it's written as a product? Well, what you can do is first, before I employ LHopitals Rule, I'm going to take the natural log of x and divide it by 1 over x. Okay, so then in this case, what do I get when I do direct substitution? I get negative infinity, as we saw before, and here I get a positive infinity. 1 over 0 technically is a positive infinity. Therefore, what I can do is I can do LHopitals Rule, because I get this indeterminate form. Write that, please, otherwise you will lose a mark. No point in losing a cheap one. Okay, so the derivative of the top is 1 over x. Derivative of the bottom is negative 1 over x squared. Okay, oops, and I didn't want that to be infinity. I don't know why I did that. I want that to be a 0 coming from the right. Okay, now I'm going to simplify this by multiplying by the reciprocal of the denominator. Oh gosh, I'm obsessed with infinity right now. If I multiply by the reciprocal of the denominator on both top and bottom, negative and negative, right, what I will get is x squared over x. Okay, and when I do a direct substitution of 0, I get negative 0 squared over 0. Wait a minute, that's a problem. Why? Because guess what? I can reduce. So negative x squared over x comes out to be x over 1. Alright, you could have employed LHopitals Rule again. Instead, I'm just going to distribute, or I'm going to go ahead and reduce, and so therefore the original limit would be 0. Okay, let's move on. Let's do one of these problems from the homework. Okay, so let's look at B here real quick. If I did a direct substitution, that'd be 1 over 0 minus 1 over 0, which is the same as infinity minus infinity. So if I can combine this into one function as a rational function, then I could use LHopitals Rule. So let's go ahead and do that. Let's get a common denominator. Let's multiply this side by x, top and bottom. And let's multiply this side by sine 2x, sine 2x. And so I would have the limit as x goes to 0 from the right of, it looks like sine 2x minus x over x sine 2x. Alright, and direct substitution of that is going to be no different than what we just got. It's going to be 0 over 0. So let's do LHopitals Rule here. And if I do LHopitals Rule, it looks like I would get the limit as x goes to 0 from the right of, that'd be 2 the cosine of 2x minus 1 over, product rule, okay, so that'd be sine 2x times the derivative of x, which is 1, plus 2x cosine of 2x. Alright, so let's do a direct substitution here. That'd be 2 times the cosine of 0 minus 1 over, well, if I plug 0 in here, sine of 0 is 0, plus, looks like 0. Therefore, I get 2 cosine of 0 is 2 minus 1 over 0, which looks like I get 1 over 0, which means that this limit does not exist. Okay, so I used LHopitals Rule. It just didn't work out for me, but that's what it is, right? Sometimes that happens. Alright, let's move on and try another one. Okay, let's attempt to find the following using LHopitals Rule. Alright, and number 2. Okay, so tan of 0 is 0. Secant of 0. Whoops, sorry. Tan of pi over 2 is infinity, coming from the left, and secant of pi over 2 is also infinity. Alright, so we get this indeterminate form. So I'm going to take the derivative of the top. Derivative of tangent is secant squared. Derivative of the bottom is secant x tan x. Okay, so I'm going to take the limit as x approaches pi over 2 from the left of that. First I'm going to reduce. That might make my life a little easier. So if I reduce, I'd get secant over tangent. Let's think about that. It's secant x over tan x. Secant is 1 over the cosine. Tan x is sine over cosine. Alright. However, it is technically cosine over sine because we're dividing by tangent. Cosine over sine because we're dividing by tangent. So as cosine x's cancel, I get 1 over sine x. So really I'm taking the limit of this as x approaches pi over 2 from the left. And that, if I do a direct substitution, sine of pi over 2 is 1. Therefore, that limit is 1. All right, let's do one more. Evaluate if possible. Let's see here. Let's do this one right here. Limit as x approaches 1. Well, here I get 0 over 0, so that's an indeterminate form yet again. I'm going to employ LHopitals Rule. And I get 1 over x over 1. So the limit as x approaches 1 of this is going to be 1 over 1 over 1, which is 1. Okay, cool, that one worked out. Oh, this one will be an infinity over infinity. Again, indeterminate form. L'Hopital says derivative of top, derivative of bottom would mean that this is the limit as x approaches infinity of e to the x over 1, which, go figure, is still infinity. Therefore, this limit does not exist. Okay, I'd like to look at this one. This one is funky. So I'm going to write a few things down. I'll come back and explain. Okay, so if I do a direct substitution, I get infinity to the 0, which is an indeterminate form. But how the heck do I go about working with this to get this into a form that would be rational in nature? Well, here's what you do. This is really weird, but you're going to take y equals x to the 1 over x, and you're going to take the natural log of both sides. Taking the natural log of both sides allows you to bring this 1 over x down in front. So I'd have natural log of x times 1 over x, right? Times 1 over x. Now I'm not going to write it that way. I'm going to write it as this. Now I'm going to hang on to this piece over here for later when I evaluate the end of my limit. Okay, but I'm going to take the limit as x goes to infinity. I think it was infinity. Yeah, it was infinity. Okay, and in this case, I'll get infinity over infinity. Right? Which, of course, is an indeterminate form, which allows me now to use LHopitals Rule. So I bring this natural log of y along with. I still have the limit as x goes to infinity, but now I have 1 over x over 1. Okay, so what would this go to? If I do a direct substitution, plug in infinity, I get 1 over infinity over 1, which is equal to 0. Okay, so what I have is that the natural log of y equals 0. And y represents the value, the output of the original function, right? Therefore, the limit will follow this. If I take this in exponential form, I'm really just looking for y. And what does y equal? E to the 0, which is 1. Therefore, the limit as x goes to infinity of x to the 1 over x is equal to 1. It's a really cool one. This would be more of a bonus type. But that's it. LHopitals Rule. Get everything in rational form, make sure it's an indeterminate form, and take the derivative of the top and the bottom. See you next time.